All right, and in our final talk in the session, this session feels a little bit for me like getting the band back together, because some of the folks I've worked with back in 2011 on Kepler, using those expertise we've learned on Kepler and TESS and bringing them to Roman. So Avi and I have worked together for many, many years, so off you go.
And we were having fun most of those years. Okay. So it's been, I hope that it's okay if I say it's a consensus that Roman will detect many planets, and in this talk I'm focusing on hot Jupiters. So Roman will detect many transiting hot Jupiters, but the huge challenge, which also Robbie referred to earlier, is how do we tell the difference between the false positives and the real planets, which is also a huge problem in any transit survey from the ground and from space. It's not a new problem, but it's a different version of the problem because of the Roman band. So what I hope to show you and maybe convince you that detecting the atmospheres of these hot Jupiters, and again, I'm focusing only on the hot Jupiters, we can differ between the real planets and false positive scenarios. And by doing that, we can confirm or validate, we can debate the exact terminology, and also study those hot Jupiter atmospheres. And by doing so, we can study the hot Jupiters or the hot Jupiter population at the bulge, which extends by a factor of 20 or more the distance of the known population of hot Jupiters in the solar neighborhood. So I'll take you through 3 slides where I go through the details of the analysis. Obviously, it's not enough. It gives you only the highlights. We start with a Besançon model. I hope I pronounce it correctly. By hot Jupiter, I mean planets within 3 days and larger than 8 Earth radius or 0.7 Jupiter radius. I'm only talking about those kinds of planets, not beyond. And we assume or we inject 2 different or 2 independent separate occurrence rates of hot Jupiters from these papers, and then we call them method A and method B. One is more conservative, one is less, just to have 2 different estimates. We do assume a metallicity boost, given the expected metallicity increase in the galactic bulge, and we assume the corrections from Robbie's 2023 paper. These are let's call them the ingredients of how we treat the atmosphere. One thing we do is we use this empirical relation, which by now is a very well-known relation in exoplanets, between the measured or observed planet radius for hot Jupiters versus the stellar insulation, and the x-axis here is in log scale. And we also assume some simplifying assumptions about the atmospheres, which we can debate later. And this is basically our noise model, or what we assume about the noise. And what you see here is the secondary eclipse, meaning as the planet disappears behind the star. So it's a secondary eclipse depth, this is the secondary eclipse signal to noise detection in log scale and versus orbital period and linear scale. And I'll talk about detections at a threshold of signal to noise of 5 and 10, or 5 sigma and 10 sigma. And you can see that given the brightness of the star, all the detections grow smaller, or the signal to noise grows smaller as the orbital period goes, which is very much expected. One interesting thing is to compare the noise to that predicted by Robbie's paper from 2023, and that is shown here. In our paper, it's the blue curve, and from Robbie's paper, we admittedly digitally took the plot from the curve, so it's not an exact numerical value, just a visual comparison that shows they compare relatively well to within better than 10%. which was reassuring because these noise models are not built exactly the same. And here are the results. We expect ballpark of 10,000 transiting hot Jupiters, of which we can detect the atmosphere in secondary eclipse and also the phase modulation as the planet is orbiting the star and showing us the difference between the day side and night side thermal emission. Above 5 sigma, it's between 2 and 3,000, and above 10 sigma, it's between roughly 1,200 and 1,700, and these two numbers are again given the two occurrence rates we assumed, what I called method A and method B. Here is the distribution with the spectral type of the host, and somewhat surprising, or at least to me it was surprising, that vast majority of them will be orbiting G stars. This is the brightness, and brighter stars are up here, versus the orbital period. Orbital period is here in log scale, and quite expectedly, most of the detections are at very short periods. Sometimes we call them ultra short periods, within 2 days and within 1 day even. And also at a magnitude of roughly 18 to 20, which is simply where the stars are. This is the distance comparison, what I mentioned earlier. This is the distance distribution of hot Jupiters that we know of, and this is the predicted distance distribution of hot Jupiters with the detected atmosphere that we expect to get, and it peaks around the distance of the bulge, again, because that's where the stars are. And in this slide, which I'll spend a couple of minutes on, this is where I want to try and convince you we can use the signal from the atmosphere in the secondary eclipse and in the thermal modulation or the phase modulation due to the thermal emission from the planet to differ between real planets and false positives. So I have the real planet in blue and a false positive where the companion is not a planet but it's a star with a similar size, meaning radius to a planet. That would be an M-dwarf companion, that's here in red. But the M-dwarf companion, the variability is still on the target. A blended DB, it means the variability is not on the target, but it is blended on the CCD, which is extremely common false positive in Kepler and even more so with TESS. So these are the three scenarios. And the critical thing, or the critical parameter here is the ratio. The ratio between the secondary eclipse depth to the transit depth. Because the transit depth for all three scenarios will be very similar. This is why they become false positives. So the ratio for planets is pretty small. It can be as small as 10 to the minus 3. And for an M-dwarf companion, it's much larger. Simply the roughly 1 to 10, and it's even larger for eclipsing binaries. And again, this is the ratio between the secondary eclipse depth and the transit. It is not the transit depth or the secondary eclipse depth. It's the ratio between them. So it's a parameter. There is no units on this parameter. And there is a similar diagnostic we can use for the ratio between the phase amplitude of the thermal emission of the planet, because as the planet, these short period planets are tidally locked to the star, so the hemisphere facing the star is much shorter than the hemisphere facing away from the star. So as the planet is rotating, it will cause a difference in brightness along the orbital phase. This was a quick intro for non-exoplanet people, which I understand is most of the audience. So here is the ratio of the secondary eclipse to the transit depth. It's very difficult to control this thing, very challenging. Anyway, in log scale, as a function of orbital period, and for a planet, the secondary eclipse depth will depend on the period. The transit does not depend on the period, by the way. But there is no such dependency for a stellar companion, meaning an M dwarf. And for a blended EB, situation is even better. So say, for example, we measure there is a 2-day or even a 1.5-day candidate, and we measure the ratio somewhere here. That allows us to say this is more likely to be a real planet than a false positive. And if we measure it somewhere up here, that can allow us to say this is not likely to be a real planet. This is how I imagine this will work. And indeed, there is an overlap at a very short period. I'm not ignoring that. In this plot, I'm trying to show how this works for the ratios of the thermal emission amplitude compared to the ellipsoidal distortion amplitude, meaning the ellipsoidal distortion of the star due to tidal forces from the planet or the companion, and also the Doppler boosting amplitude due to the orbital motion of the star. Those ratios are much smaller for a real planet than they are for a stellar companion, simply because the tidal distortion, or what we call ellipsoidal distortion, and Doppler boosting, they depend on the companion mass. And the companion mass for a star is much larger than that of a planet by 2 orders of magnitude. And here, just to give you an idea, in blue, this is a schematic phase curve of a real planet, and it peaks around secondary eclipse, ignoring any possible phase offset. And for a stellar companion, it's the red phase curve, which is dominated by ellipsoidal distortion, which gives these 2 peaks, one here and the other one here. And the Doppler boosting signal causes these 2 peaks to offset from each other. So you see that the shape is expected to be very different. To wrap up, there are many caveats in anything I just talked about. I'm sure you were able to think about a few. The main one is that we are not working with real data because there is no real data. We don't know how stellar variability will affect this or systematics. And there are other caveats, and I should mention here, I think I'm talking here only on behalf of myself, I should be a bit maybe even humble and say that I am working with simulated data, the real data might not behave as expected. I've noticed it a few times in my own work and work of others, back even when I was a student. So, and this is why I used a relatively high threshold of 10 sigma. So, and also the numbers here are large enough, and the thresholds also conservative enough, that I hope that even in the face of real data and the problems that real data sometimes give us, this can still be a worthwhile endeavor, and we can detect a significant sample of these planets. There are many spin-offs and extensions of this study. I will skip this. You also might have your own ideas, and put this summary up, and I'll be here for almost the rest of the week. Thank you.
Thank you, Avi. That was very interesting. Hot Jupiters continue to give. Any questions for Avi? I will ask. So, Avi, I don't know exactly where the theory stands now on hot Jupiter formation, but will Roman be able to kind of inform how we think hot Jupiters form?
I think from the numbers, we can at least compare to the occurrence rate in the solar neighborhood, and the comparison will show us, I think, the differences, or will point to differences in the formation scenarios. Say that region is more crowded, so less dynamically stable, so that might mean something. And that's another reason for optimism, that the numbers are large enough that if the detection is like order of magnitude smaller, maybe we can still detect them in a large enough number and say, okay, the astrophysics here is different. Or at least that's what I'm hoping for.
Hi, Avi. Very nice talk. So, in my talk, I was very interested in the planet occurrence at the bottom of the main sequence, but there are also really interesting questions about planet occurrence on the other side of the sun, sort of A and F stars. And you said that you're mostly going to be doing G stars. You mentioned you were kind of surprised by that, but I'm wondering.
I didn't aim for it. It just came from the data.
But do you expect to have large numbers of transiting planets discovered around earlier type stars as well, compared to currently known? 20 times 20 more for the G stars. I mean, I wonder about the A and F stars, because we really don't have great constraints there.
You mean this slide? Yeah, these are significant numbers. If they truly hold, you're right. I wasn't thinking about that particularly, but you're absolutely right. The numbers here are significant compared to what we currently have. And if these numbers materialize, it will be its own smaller niche of hot Jupiters around earlier type stars, which I think there are a few people at Caltech are interested in.
Thank you.
Okay, we've got time for perhaps one more question for Avi. I don't see anything. Okay, if not, let's thank Avi and all of our speakers in this session.